The presentation today, we're talking about CO2 sequestration and climate, and I'm a laboratory fellow at the National Lab, just a couple of miles up the road here. And I have to have a confession here. I'm a sequestration researcher. Yes, I'm going to admit it. I'm a sequestration researcher. Yes, I've dabbled in geothermal. I'm doing some work on gas separations and sensors. I'm even dabbling in gas hydrates. This is the thing that's probably plugging that cap that they're trying to put on the well there in the Gulf of Mexico. But I always come back to sequestration. It's one of those things I can't just kind of shake off my shoe. I want to come back to that. So I hope at the end of the time that we have here this morning, you'll have a sense as to why. You know, why I always come back to sequestration as something that I think is so important for scientists like myself, engineers to work on, to solve this climate change problem. So let's just dive right into the guts of it here. We're talking about doing CO2 capture and sequestration to solve a particular problem, right? So what's the problem that we're trying to solve? What's that two-letter word that people use?
C02.
Yeah.
Climate change.
Climate change. There's another one.
Global.
Al Gore. Global.
I bit my tongue on saying that.
Yes. What is it again? Say it louder.
Global warming.
Okay, you said it, remember, I didn't. So that's an effect. And so when I talk to groups, unlike yourselves, who want to mention GW, I go back to the hard data itself, because GW is an effect of something that's happening in the global atmosphere. So I go back to a record like this. So if you look at this chart, I've picked a time frame from 500,000 years. You could pick another time frame. You can get data that goes back much, much longer than this. But the basic story is that you've got CO2 concentrations that are sort of oscillating, but they're around 200 up to about 270, 280, maybe 300 parts per million. And this scatters back over a very, very long period of time until we get to the Industrial Revolution right there, and then kaboom. It's just a straight shot. We're up here right now about 385 parts per million and going higher. So that's the facts. That's the part that I always want to go back to. These are just numbers. So always the question becomes, okay, if I say that's a fact, so how do we know that these are just data? These are just numbers. How do we know? I mean, looking back over 400, 500,000 years, there obviously wasn't a technological society that could give those data. How do we know this?
Take ice cores.
Exactly. Exactly right. We take ice cores. So those ice cores, when the snowflakes were falling in the Arctic, they encapsulated the atmosphere at the time, and that gets buried into those ice sheets. And those little gas bubbles are present when we drill down back through and get those ice cores and pull them back up to the surface, put them in a mass spectrometer, and we get the snapshot of what the atmosphere was like at that point in time. These are just numbers. And so we know exactly what the atmosphere was like looking back over 500,000 years or even longer. How do we know how good this is? So if we kind of really magnify in and we look at the last 1,000 years or so, we began collecting, and the resolution here isn't probably good enough for you to see, but we began collecting atmospheric CO2 concentration data at Mauna Kea in Hawaii in 1956 or so. And if you look at the data from the ice cores versus the hard numbers that are coming from the observatory there in Hawaii, they're perfect. They stitch right together. So we know exactly that those data are good. And we're doing this global experiment in terms of putting more CO2 into the atmosphere than can be absorbed in the global carbon cycle. So this is the part I always come back to. You can get to arguments about the effects, global warming. The bottom line of everything is once you finally kind of get beyond this sort of natural cyclic variations, is that what we're doing by burning fossil fuels at the rate that we're doing is something that hasn't happened in many, many hundreds of millions of years on the planet. And if we do go back very long periods of time to get to levels that we're going to approach, this world looks a lot different than we have right now. We've got sort of subtropical areas in the Arctic region, in Alaska. We know this from the geological record. So that's kind of where we're headed if we don't do something about this from a business as usual standpoint. That's actually what's on this next slide. So if we look at this and we think about, okay, are we going to do something about where CO2 is heading on a global basis? And what the analysis, this is some results that come from the Joint Global Climate Change Research Institute at the University of Maryland. We have a collaboration with our colleagues there. What it says is that if we're going to decide globally, we're going to cap CO2 concentrations at some number, be it 450, 550, 650, or 750 parts per million, the profiles are all the same. CO2 emissions have to peak and they have to decline over the balance of this century and beyond. So the question really becomes, all right, if that's what has to happen to hit some kind of global CO2 number, what do we do from a technological point of view? What do we deploy to try to hit that? And that comes from this curve that you see down here. The basic story is we need everything we've got in our energy portfolio. We need conservation. We need renewables. We need wind. We need nuclear power. And also what we need is if we're going to continue to use fossil fuels, particularly coal and natural gas, then we've got to implement carbon capture and sequestration, or so-called CCS. It's the last wedge that you see here on this chart that makes this picture whole to hit, in this particular case, 550 ppm. So can we get there if we say we're not going to use fossil fuels? The answer is yes, we can. The issue is cost. How much does it cost to get to the same place if we massively deploy more nuclear or biomass energy sources or much more wind and solar? And so it's always a question of cost, and the numbers come out to many tens of trillions of dollars if we forego the use of fossil fuels to hit those targets. So this was a really powerful message for me, and why back in the 1990s I began working on this problem, thinking about this. How can we use technology to hit some of those curves and continue to use fossil fuels to support our economic development?